So what is big O? Big O notation is special notation that describes the performance or efficiency of an algorithm. In other words, it's a way to tell how fast an algorithm is. Big O notation allows us to describe how the runtime of an algorithm grows as the input size increases, given as a way to compare and analyze different algorithms based on their efficiency. So let's have a look at a list of the most common running times for algorithms using big O notation, along with the examples. And the first one is going to be big O of 1, a constant time. The algorithm takes a constant amount of time regardless of the input size. So it doesn't matter how big the input is, it always takes constant time. The examples will include accessing an element in an array by index. When we know the index, we can access the element in constant time. Performing basic arithmetic operations such as addition, subtraction, multiplication, or division, or returning the first element of a linked list. We also do it in constant time as we have a reference to its head. The next one in our list will be big O of log n, or logarithmic time. This algorithm's runtime increases logarithmically with the input size, as you can see here in the graph. And the examples will include binary search in a sorted array, or finding an element in a balanced binary search tree. And both of those cases are considered to be big O of log n complexity, because in both of them we can cut the search space in half, as we do in binary search or balanced binary search tree. The next one is going to be big O of n, or linear time. The algorithm's runtime grows linearly with the input size. And the examples will include iterating through an array to find the maximum element, counting the occurrences of an element in a list, or linearly searching an unsorted array. In all the cases, in the worst case scenario, of course, we go through the entire array, so we do it in n time. N time here, n time here, and n time here as well. The next in our list is big O of n log n, or linearithmic time. The algorithm's runtime grows in proportion to the product of the input size and the logarithm of the input size. And the examples include sorting that utilizes a divide and conquer strategy, such as merge sort, where the input is repeatedly divided into smaller subarrays, which are then merged into a sorted manner, or quicksort, which partitions the input based on a chosen pivot element and recursively sorts the resulting subarrays. The next on our list is big O of n squared, or quadratic time. And the algorithm's runtime grows quadratically with the input size, as you can see here in the graph. The examples will include selection and bubble sort. In each iteration of those, these algorithms compare or swap elements within the array, resulting in quadratic growth as the input size increases. Another example is nested loops iterating over an array. Now, let's have a look at big O of 2 to the power of n, or exponential time. The algorithm's runtime grows exponentially with the input size. And examples will include algorithms that involve permutations of a set, where the number of possible permutations grow exponentially with the size of the set. And the last big O notation complexity we're going to briefly cover is big O of n factorial, or factorial time. The algorithm's runtime grows factorially with the input size. And the examples will include traveling salesman problem, where a salesman needs to visit all of the cities, and we need to find the shortest possible route that visits each city exactly once and returns to the origin city. So we can see that big O helps us understand how different algorithms scale and perform as the input size increases. Among the most common running times represented by big O notation, some algorithms are better in terms of efficiency, while others are worse. Algorithms with high time complexity, such as big O of n log n, big O of n squared, big O of n to the power of n, or big O of n factorial, are not considered efficient. Their runtimes grow significantly with the input size, making them less suitable for large-scale problems. These algorithms may become impractical to run efficiently as the input size increases. Algorithms with average time complexity, such as big O of n, are considered quite efficient as their runtime grows linearly with the input size. However, algorithms with lower time complexities, such as big O of log n or big O of 1, are considered more efficient as their runtimes remain constant or grow logarithmically with the input size. These algorithms are generally preferred when dealing with larger datasets or performance-critical scenarios. So knowledge of big O notation complexity helps in technical interviews by demonstrating your understanding of algorithms' efficiency and your ability to analyze and optimize code.